Thank you, Namir. It's a pleasure to be invited to your farewell session, and I thought I'd actually begin by just reflecting on part of my backstory in getting involved in the Wellington Structural Group all those years ago, before I get into a couple of themes of contemporary practice. I was 3 decades ago, I was a relatively young graduate engineer working away designing multi-storey buildings in Wellington, one of which is on the left-hand side of the screen. Yes, it was a ductile precast concrete building with precast concrete floors, nominal seatings, the way we did things back in those days. But and then I would regularly attend the meetings of the Wellington Structural Group, because that was the place that young engineers got to, and not so young engineers got to understand what was going on by other practices, site visits, as well as presentations in the middle of a building boom. And then one day out of the blue, the then chair of the Wellington Structural Group, Peter Leslie, who one or two of you will know, who was the chair, asked if I would take over from him. And that was somewhat out of the blue. But I spent a couple of years in that role, learning the ropes, just as Namir said. You've got to find speakers, you've got to set things up, and you've got to do a bit of the introduction and farewell. Great, professional development, and that set my career off in a lot of different directions. It got me to meet Barry Brown, because in the late 1980s was when Barry put the wheels in motion to create SESOC, and that's led a profession-long collegial relationship that we enjoy to the present time, and a number of other friendships. So in acknowledging Namir's valuable contribution as chair, I hadn't realised till tonight just how many years he's been on the ASG committee, he's I know whenever Namir has lined me up for a presentation, I'm never going to get away from that, and whether it was a case of polite persistence or persistent politeness, he would always bring me to the podium. Again, it's a great pleasure to be here in acknowledgement of this situation. So the segue between the 1980s and current practice actually takes the form of the Newcastle earthquake. And last November I went along to I'm a member of the Australian Earthquake Engineering Society, went along to their annual meeting, which was the 30th commemoration of that event. I had been quite closely involved for 4 years after that event, when I was working in Sydney before I came back to New Zealand. And but one of the keynote presentations was in relation to the site which was their CTV building. It killed 9 out of the 13 people that lost their lives in that event. Basically, it was compared to all of their unreinforced masonry buildings, that was actually a concrete frame structure with a lot of masonry in it. Professor Rob Melchers, that some of you may have heard of, one of the doyens of University of Newcastle, he was tasked with leading the analysis of what caused the collapse. And he produced a report several years later that was only released to the profession on the 20th anniversary of the Newcastle earthquake. And so 10 years on from that, he was reflecting. Amongst the presentation, one of his key reflections was that homily, that the investigation of building failure invariably focuses on the technical issues, but the importance of competent checking by experienced engineers usually emerges as a key factor. So hold that thought as we fast forward to 2019, where again the design of more than one multi-storey building, let's just say, has been found wanting last year, and some of the issues are actually popping up in other spaces, and I just wanted to convey a few thoughts on that without dwelling in any detail on any of those buildings, obviously, but there's some areas of challenge and opportunity that I want to just run through with you, and we'll phrase them as engineering practice issues in 2020. There's a lot of discussions going on in this space, and I'll just add some thoughts into it. But the three themes really, it's all around the designing of ductile structures, and again, what we're seeing is some disconnect between concept and detail. Linked in with this is the PS2 Design review process that we all love in our different ways, but it needs to be made to work better as part of a broader quality assurance process. And along the way, it's all about increasing our collaboration. And that's the diagram on the right-hand slide of my first slide that so I'll come back to. But what might increasing our collaboration at the design level look like? So the common threads from those recent design failures, again, that mainly pertain to, I'm talking in the domain of ductile multi-storey buildings. It's the old chestnut of inter-storey separations either not being provided in terms of floors being locked up between floors, or the building separation between adjacent buildings where the numbers haven't been done correctly and not enough space is being left. The fact that the design process starts by assuming a level of ductility to determine the structural loadings, but that's not followed through. The talk is not walked when it comes to the details. That plays itself out in the most notably in steel space around column splices and the bases of columns, foundations, not properly taking account of overstrength actions, and the associated element detailing not meeting material standards or the relevant guidance. And again, sometimes the question remains, was the concept wrong or not sufficiently thought through is perhaps a better way of putting it, or the detailing not followed through appropriately. Carrying on, the third common denominator is that in each of the cases that I'm aware of, it was subject to a full PS2 design review. It just didn't spot those shortcomings. The common consequence of the ones that I've been associated with is that the cost to everyone, well beyond the design team, of getting the concept and the detailing or any combination of those two wrong is vast. And these are their design failures, but they were picked up in various stages of construction. And I think we can all think of one or two in this space. Talking about, and I'm mixing these themes as I go through, but let's jump into the PS2 review process and again link that with QA. But what we're typically seeing is that PS2 reviews they're seen as a compliance element, invariably undertaken upon completion of the design, and they're typically procured on the basis of price. That's a sad bit of reality that we're all conscious of. And so if that's the process element, the process aspect around a PS2 review, then you have the technical aspect that some PS2 reviewers are just not seeing the issues with the load paths or where capacity design requirements are clearly not being met. And again, that's a technical competency issue that's playing out. Again, whether that's a consequence of it's one of the consequences of detailed design drawings being so well developed and so complex that some of the PS2 reviewers are not standing far enough back and examining the structure as a raw skeleton, I guess. So what's the linkage with quality assurance? And I was discussing this with Tanya Williams, General Manager of Engineering Leadership at Engineering New Zealand, and she jumped in straight away and sort of said, well, we all know that QA is most effective at the 10% stage, and you can debate the number, but QA is most effective at an early stage. This is actually a theme, the themes around QA will come out in the Engineering New Zealand systems report, which some of you will have read around in various information releases. It's still a few months away, I think, but dealing with a whole lot of things in the quality space. But the particular kite that I'm keen to fly here, the suggestion is that is there anything wrong with involving the PS2 reviewer at the end of the preliminary design phase? Because again, I know if I was still doing design these days, I'd be really wanting to make sure that I had the concept of my structure, at whatever stage I developed it to get it cleared and confirmed. Whilst it might not need to be done in a regulatory frame then, having the same PS2 reviewer who I know is going to then put my design through the paces at the end, to have given it a measure of tick at the preliminary design phase would give me a great deal of comfort. But also, in that QA sense, that's the right time to identify all the issues that the detailed design must then go on and address. Don't leave it to chance that the design engineer is actually sufficiently au fait with all the complexities of detailing ductile structures. And so it's a golden opportunity, it seems to me, to actually set the path to completion. So again, at the end of the preliminary design phase, these questions should be covered off. And a lot of the analysis questions go back to the regularity of the structure. Is that clearly understood? Just make sure it's not an irregular structure driving different analysis methods, and not leaving that vague as we enter the detailed design phase. As the design develops to the point where the separations in the primary structure are identified, they're where they need to be, and they're not, then they are appropriately generous proportions, not squinted. Because once you go into the detailed design stage and you haven't got your separations right, hard to pull back from that. Equally, that's the time, what are the detailing objectives? What are the detailing requirements? Particularly, reflecting what we see, what's the rationale for deriving the overstrength loads? It varies from material to material and type to type. But the notion is, if you put a box around those three, map those out, state them in a brief version of the design features report as a preliminary design stage deliverable. It's a requirement in some spaces, such as the Ministry of Education through their various review stages. I think that could be adopted for any building. I'm just going to, so those are the key points I wanted to float, and I just wanted a quick sidebar into seismic assessment, because more buildings are being closed as we speak as a result of low percent NBS ratings. I just wanted to share some of the messaging really around that we are keen to make sure that engineers are across, and also try to bring this out in a more public arena, that what does a low percent NBS rating mean, what doesn't it mean? What it means is it's there, the purpose is to definitely signal heightened risk in the event of earthquake occurrence, and to get the message that some mitigation work is required, and sooner rather than later, if the building is then determined to be earthquake prone, a formal linkage with defined statutory timeframes, which are not tomorrow, they are, particularly in this neck of the woods, in terms of decades. They're not intended to signal the building is dangerous. They're not intended to signal the building is likely to collapse in a moderate earthquake. There's still a lot of legacy thinking around that from the previous EPB regime. Most importantly, they're not intended to lead to people not continuing to access and occupy the buildings before a mitigation plan and timeframes can be developed. And having invoked the notion of decades, if an issue is found with a building such as a precast floor issue, obviously don't wait decades. The owner needs to get on with the mitigation of those items within a year or two. But in the meantime, there's nothing wrong with the building continue to be occupied. We just have to do a better job of conveying this risk concept to people, where they are sadly being driven, we think, by health and safety concerns, let's just say, erroneously. But just wrapping up, just to reconsolidate the points I'm trying to have a wider discussion on, and that's as we go from the concept or the preliminary design level towards detailed design, treat that more as a hold point in project management lingo. It's also a collaboration opportunity. It's asking the broader question, has anyone else with experience, either from within or outside our practice, had a considered look over our design? Are we clear on the critical design and detailing provisions that must be met in the detailed design? And get that early engagement of a PS2 reviewer. It can only be beneficial. They can still have an early engagement and be independent as required from a regulatory perspective. And to come back to my opening little diagram there, structural group participation is still one of the best ways of getting the broader knowledge, not at the detailed design level, but the broader knowledge of what's going on, what our colleagues are up to, sharing our understanding of what makes good design, and the issues from seismic assessment. And that diagram is my representation of what collaboration is trying to do, trying to reduce the spread about the mean of professional views. Thank you very much. Sure, and in Wellington, it's in particular, it's being perceived as a factor in, firstly, whether they will insure, secondly, how much they'll charge for the cover, and that's our beloved free market. That has to play out. But again, insurance, and that's tough, and it's particularly tough for body corporates and in some of those situations. It shouldn't cross over into occupancy, but it is being used by sectors that don't appreciate the percent MBS is only a life risk perspective, not a damage perspective, which I think is the point behind your question.
But it goes into the cultural belief that if insurance does not want to cover, there must be something wrong with that building, and then.
Sure, but that doesn't explain why councils that own buildings in some places are closing them upon receipt of a low rating. It doesn't explain why government departments are not occupying. But it is another factor in the environment.
Are they dead scared about the occupational health, safety and health job?
They are, and we've working with Engineering New Zealand who have spent a good bit of time trying to, how can we communicate this better? Fairly clear that it's the director's risk perspective that the wording in the Health and Safety and Work Act, when it speaks of a risk that can be mitigated with the implication that it should be, a building with a low rating, if you take the director's perspective, you can take the view that, well, we should be mitigating the risk by not occupying the building. That we feel there's a disconnect, but it is absolutely in that space. Okay, thank you.
Thank you, David. Our second talk by Paul Campbel, Professional Challenges Facing the Profession. Paul is a technical leader at WSP, two decades of experience in structural engineering. He's past chair of AAP.
You don't have to read it all.
Also, he's past SESOC president, and life member of SESOC, and a fellow of Engineering New Zealand. I'll leave it to Paul Brunsdon. Thank you. All yours.
Thanks, Namir. I'll say a few words to you towards the end, if I may. So you've all seen the synopsis. So I've done a complimentary presentation to what Dave's done. It's not technical in any way, shape or form. I want to focus more on behaviours, professional behaviours and some other things. So the first thing I want to do is I want to talk a little bit about communication. Engineers don't often get up and talk about communication, but if I put a whole lot of icons up there to represent that we communicate in many ways, and in my opinion, we don't necessarily do a lot of them that well. So let's just explore that. So the first thing I want to sort of touch on is how do we communicate performance? And I actually don't want to talk about structural engineering, I want to talk about the car industry. I just went on to Google and they are two ads for a Volvo. One, the bright shiny thing there, and the next one is the crumple zones. They are preconditioning purchasers that these cars, if they have an accident, will get written off. They don't do it in a doom and gloom fashion, but they give the information out there. And you know, it's quite nice in sort of an engineering way, but how many of us can actually say that we really talk to our clients about what we are designing and the performance expectations under an extreme event? Christchurch was a shock to everyone. We talked about insurance before. You know, the insurance industry was surprised at how many buildings had to get written off. So Joe and Jane Public, they were surprised. So I just want to sow that seed. We've got many ways of communicating, and we don't necessarily like to think outside the box. So the next example I want to give you in terms of communication has got something to do with risk, and Dave's already touched on that, and it's communicating risk through art. So there's an artist, based in America, Susanna Hirsch, and she has explored risk through art. And this is quite a telling thing. I've actually adapted this picture, which I'll show you in a minute. But we've got a horizontal line there, and we talk about, you'll have to excuse the Americanism, public outrage versus actual hazard. Now, I hope I'm not offending anyone from Christchurch. Let's talk about a terrorist attack. The actual probability of it is so low it's not funny, but the outrage is massive. Compare and contrast that with cancer or a car accident. What happens, and there's no science to this, I just guessed the size of those dots. What happens if we're talking about an earthquake? You know? So let's just get a little bit real about how we do communicate things. So we've made this really bold decision that we want to communicate risk and we want to communicate performance to our clients. So we've got an example here of art. We've got a quite a cool example here graphically from the car industry. So what do? We show disasters. We show things falling down. We almost communicate by alarmism. You know, why can't we stick a fantastic picture up of a great piece of structural engineering and then use that to explain performance? Why do we always go back to our failures? Sure, we need to get across to our clients that we are designing for life safety, if that's what we're doing, and there will become a point where perhaps collapse is more than a real probability. You know, it's highly likely. But why do we go straight to henny penny and chicken licking and the sky's falling in? So that was my sort of view of how we might communicate performance to our clients. Let's showcase something seriously cool. So still on the communication theme, having decided that we do actually want to come out of our shells and communicate to our clients, how do we go about doing it? We've got all these medians. So what we choose to do is we choose to talk about TWAs. So I'm going to tell you a story about TWAs, and this story goes back sort of 20 or so years, well, actually more years than I care to admit, when I was at university. And my professor walked in and said, today we're going to talk about TWAs. It's like, great. And he got about 15 minutes into this lecture about TWAs, and someone stuck their hand up and said, excuse me, what's a TWA? They got a duster thrown at them, because you could back then. I'm glad you bloody asked. A TWA is a 3-word acronym. Now don't ever sit there like a stoned mullet and not ask a question again. Now look at our TWAs. I showed that to my wife. I might have showed it to a toddler for all the meanings. We talk about ULS. What does ultimate limit state actually mean to our clients? And if they get that, what does serviceability limit state mean to them? And then we've got a 1 and a 2 of them. We've got a percentage MBS. We've got an MCE, a DBE, an ISA, a DSA, a DEE, a slammer, a ding-dong bammer, for all I know. Seriously, when we talk like this, do we expect the audience to understand what we're on about? We have enough debate internally about what NBS means. So once we get out of our TWAs, we talk about jargon. Now, plastic hinge, great. What's that? I mean, that's what I get if I say that to a client, if I say that to my grandmother. Overstrength, yeah, that sounds good. Sounds like we need some of that at the gym. Non-linear time history. When was the load living, let alone dead? You know, people don't get these. So I know this is recorded, I thought very hard about this. I put my own 3-word acronym up. But at the end of the day, we might as well just be talking alphabet soup to people. Now, you know, I'm trying to make light-hearted of all this. This is a serious issue. How many of our reports are littered with this stuff? You know, those people that do a design features report, thank you. Everyone should be, but thank you for doing it if you are. But when we talk about some of this stuff, how are we actually conveying the message to our clients and knowing that they understand it? How are we conveying this message to other disciplines and getting them to understand it? So I'll get off my high horse on communication momentarily. Hands up who's never made a mistake. Great, I thought someone might stick their hand up. So we've accepted mistakes happen. Do we think they happen in our designs? Hell yes. So if we accept that we all make mistakes, and I'd be surprised if that's not a true statement, I've borrowed this first bullet point off somebody. Is it something that could be a tolerable imperfection, or is it an intolerable error? i.e., we've got all these factors in our designs. Is it going to bring the building down? Or is it something going, you probably should have done better, but, you know, think we've got a safety factor, we'll get away with it this time. So how do we think about tolerable versus intolerable? Think about a hierarchy of failure. It's capacity design. It's kind of what we do, you know. And then if we start to think about the hierarchy or seriousness of the mistakes that we're making. Dave talked before about PS2s and checking. The last thing I check when someone gives me a design to check is the calculations. The first thing I want is the drawings. And then I look at the drawings and I go, oh yeah, I think I can kind of figure out what's going on. And I'll get the design features report, if there is one. And if I can pick from the drawings what I think the structural system is, and the design features report agrees with that, it's a bloody good start for me checking. Would it be okay to not have a clearly defined load path? Is that an intolerable error, or is that a tolerable imperfection? Because the amount of times that I see load path issues is, well, yeah, anyway, I won't dwell there. Is it okay to follow through, oh, that's a bit of a bad England. Is it okay not to follow through with the design philosophy? Dave's touched on this before. So you've gone to ductility 6, woohoo, because then your SLS 1 is all sweet and everything's just absolutely pruned to the bone. But you haven't detailed for ductility at all. You know, these things are fairly basic. It's really, really important, and that's why that design features report that Dave alluded to is so incredibly important. So we've made a mistake. We can learn from it. What do? Do we fix it? Do we ignore it? Do we try and justify it with a non-linear time history? Do we defend our answer to the hilt? Or do we act professionally? I've made some monumental mistakes in my career, and those that I have fallen on my sword over it and gone back and fixed, the client might have been grumpy at the time, but that's been a client for life, and they have thanked me for doing it. How we act is so important. So I'll get on to another little hobby horse of mine. Professionalism. Words like respect, integrity, ethics, honesty, they might spring to mind when we talk about professionalism. They're important words. They're really important words. I've got a quote here from a David Meister. He's a doctorate at one of the Harvard business schools or something like that. Professional is not a label you give yourself. It is a description you hope others will apply to you. Have a think about that. We hold ourselves up as professional engineers. It might be slightly arrogant to say that we are professional and we are honest and got integrity and all the rest of it. We earn that by our behaviours. So just to cut the quotes out of a dictionary, professional is about conduct, it's character, it's behaviours. And I also like the one when they talk about a profession being a calling that requires specialist knowledge and academic preparation. That's what we do. So, that gets me on to my next one. Who sets the risk? We had a discussion before about MBS. How many reports have you seen recommending somebody evacuate a building? If you write those reports, please don't. It is not up to us to accept the risk. How many people here, if I said I've got a 33% MBS single-storey timber-framed building, or I've got a 45% MBS precast multi-storey building, who would go into the timber one versus who would go into the concrete one? That's my call or your call in terms of risk. So, should engineers set risk? Maybe we should do something avant-garde, like actually ask the public what risk they want. Because I can almost guarantee you if engineers set the risk, it would look something like that. I probably don't actually need to say any more about that slide, but I will. It's really important that we understand we're in a learning profession. Unfortunately, when it comes to seismic stuff, we learn after earthquakes, and we learn the hard way, it would seem. But because we're in a learning profession, we should embrace that. We should accept it. We shouldn't let it stifle innovation. That's when getting, expert peer reviews. That's when getting some, commissioning some research. All of that comes in. It's really important that we acknowledge we're in a learning profession. We acknowledge that we're probably going to make some mistakes along the way, but how we deal with it and how we communicate it is paramount. I've written a note here, learn from your mistakes, because I thought I'd better emphasise that again. How many of us fear a peer review? I know when I was a graduate, I was like, God, someone's going to do my work, they're going to find something wrong. Oh, no. Now, I get really grumpy if someone won't peer review my stuff. I would much rather one of my errors be found out on a piece of paper before there's any real consequences. And the other thing I want to say about learning, it's a lifelong concept. You're kidding yourself. If you are a practicing engineer and you are not learning, you're not doing your job. I'll get off that hobby horse. I'm a bit of a bogan, so most of my things are car related. I've called that Back to Basics, and I wanted to talk a little bit about black box engineering here. When was the last time anybody used more than one analysis program to analyse their building? When was the last time, before you got the results out of ETABS or whatever, you sat down and you did some hand calcs and you roughed it out and thinking, geez, I think it's going to be this, I'll use the computer program to check what my gut's saying. Who gets an ETABS program, or who gets, no, actually I won't pick on ETABS, who gets a computer package and gets a wad like that full of numerical output? My grads know that if they give me a wad like that of numbers, I'll throw them at them. Give me a deflection, give me a bending moment diagram, give me a shear force diagram. And if I can't figure out what the hell's going on there from those things, either I've got a bit more rusty than I'll care to admit, or there's something going on. I think we lose sight of the difference between being an engineer, the creativity, the art side of it, versus just the sheer number crunching, analytical side of it. So if there's one thing that I would implore Don't do black box engineering. I mean, I know sometimes it's a damn sight quicker to use the computer program and all the rest of it, but just every now and again, break a calc pad out, a calculator out, prove that you've still got the skill set. And while Cam's in the room, I'll say hi. He's got some famous hands doing the slammer on that training. Things like that are really good because you need to understand how your structure is going to behave in your bones before you can be damn sure about how it's going to behave when Mother Nature gets hold of it. So I will get off my high horse now, and I'll put a mugshot up. I just wanted to say to Namir, 16 years, yes, you did serve on the ASG when I was there. 20 plus lectures a year for the last couple of years, that's a big ask, almost too much. But on behalf of the community in Auckland, thank you. These evenings are so important to the profession and the sharing of knowledge, the camaraderie, and I thank you for your stewardship over the last 16 years. Sorry, Dan, 2 minutes late. Yeah, 3 minutes late. Sorry, Dan. Yeah, Cam.
Can I ask a question?
Of course you can.
So Paul, your question about who should set the risk, and you say not us, it should be the public. So this is just my thought. The public out there will make up its mind.
Yep.
But wouldn't the public should deserve an informed decision? Like
Absolutely.
engineers, scientists have a role to talk to our communities, talk to our client, and give them the information. So in a way, we can't abscond from that. So we can't
Correct.
set the risk, but we got to be there to tell them, what is the risk. Like if we don't speak up for road accidents or earthquakes or dangerous building, who would? Then the next risk will be corona, and the doctors do that.
Yeah, absolutely.
Engineers have a role to play. So what's your thoughts?
Look, I totally agree with you. It's part of that communication thing. We should be articulating what the risk is to the client and giving them some scenarios, perhaps, and some options. And you go away and think about it, ask me questions, come back and tell me what you want. But we also set risk through code committees, for example, and that's not really publicly debated. Yes?
But isn't it because sensational news sells magazines, and that's what the media focuses on. And then you might have risk, but as soon as someone actually dies, then it's outrageous.
That's a whole nother 20-minute talk on the media.
It might have been a small risk, but when it actually happens,
Yeah.
no one's happy about it.
Absolutely. But people, I deliberately showed the car photo. People are conditioned that if a car is in a decent prang, it gets written off. Everyone says, decent earthquake, building written off. Jesus, that wasn't that great, was it? Why not? That's exactly what we designed it for.
Yeah, but it's when the people in the car get written off, people in the building get written off.
True.
That's a very rapid place.
True. More than happy to speak afterwards, but I have eaten now 5 minutes into Dan. Sorry, mate.
Okay, I know everyone's trying to get away, so I will keep it brief. I did think the third speaker I might get stitched up. So
Our last speaker, Daniel Crocker, will speak on water beneath the bridge. Daniel is a specialist bridge design engineer in masonry structures studio. I'm not going to read his bio, but I'm going to read something which he preserved based on what he did to the age. The very much for these presentations. That's great. So I'll leave it to Dan to write up tonight's talks. Dan, thank you.
Thanks, Amir, and thanks for all your help. Right, okay, we've only got a certain amount of time, and I realise you all want to get away to your family, so I'll try and zip through where I can. But we are going to talk about bridges, which are pretty cool. So we're going to talk about the water relief bridge.
Where is it?
No, that's the mic.
Oh, okay. Oh, I see. Yeah.
Sorry, I probably should.
Yeah. I was like, Okay. So I'm just going to cover, I mean, like I said, I will zip through this. If you want to go back over this content, it is being recorded. So I'm going to look at the overview of why we had a bridge where we needed it. Talk briefly about the bridge form. Then I want to focus a bit on sustainability and material choices and how we can influence that as engineers. Then I'll talk about some of the kind of the structural modelling and some of the analysis we used. And then I'll briefly cover pedestrian vibration and aerodynamics. Obviously, each one of those in themselves is an hour lecture. And then I've got some cool photos at the back that show you start to finish how to build a bridge. So we may zip through some of the core content. So the water relief bridge is down in Dunedin. It's right on the waterfront. If you know Dunedin, you'll know the Forsyth Bar Stadium or the Otago Stadium. It's right next to that. So it's a coastal environment. The client was Dunedin City Council. Being a cycleway asset, it was also jointly funded by NZSEA. Constructor for the project was Edifice Contracts. Geotech was Geosolve. And DC Structure Studio, we were the bridge architects and bridge engineers. And the overall project was a design and construct led by Edifice Contracts. So when we came in, the specimen design was for a very industrial, mechanical looking truss. It was purely a functional asset. When we were brought in, our goal was to come up with an alternative that would be cost effective. So we developed a cable stay concept. Primarily what we were looking to achieve here was looking at a lightweight structure that was cost effective. Now, obviously, this is well beyond what Council had originally envisaged. They were looking purely at an industrial structure that was just down by the waterfront for access. As soon as they saw what we could provide them, discussions talked about further embellishments. So there was architectural lighting added, we embellished the balustrades, and they got a much higher end product than what they originally set out to do. Again, because we actually massively undercut the budget, which they thought was okay. But by coming up with the right structural form and being very clever with our material choices, we were able to open the doorway to looking at more of a kind of a landmark. So it's a 45 metre by 3.5 metre cable stay cycle bridge. It's designed to the NZTA Bridge Manual version 3, 5 kPa live load. The mast is a 22 metre high, what we call inverted Y. So if you imagine a capital Y, it's just upside down with the bridge passing through the legs. And that's formed from steel, hollow, circular sections. It was all butt welded, so it's a very seamless architectural element in its own right. We've got 12 sets of strands for the main span and 6 on the back span. They're high-strength spiral strand cable. Being a coastal environment, they've got a Galfan coating, which is 95% zinc and 5% aluminium, just to give it that extra level of durability. Now, in terms of the superstructure, what you can see there is that's glue laminated timbers with a glue laminated balustrade. I'll come on to that next. But underneath all that, there's a steel superstructure skeleton. Now, the reason we did that is so that during construction, the superstructure could be lifted into place in one element. So there was always a safe platform to work from. Then we designed that for its own dead load plus a little bit of live load to allow 2 people to go out with safety lines and erect 2 of those cables. Once 2 cables were stressed, we could then lay all the decking and then progress the design. Once everything was on, we could then stress the remaining cables safely. That's probably enough on that. Now, I want to cover sustainability. Now, I often get asked, how can we as engineers influence sustainability? Now, we've got a bit of responsibility to our clients for coming up with section sizes and materials. And it's in our material choices that we can really make a difference. So in terms of making this competitive, it was about lightweight structure. So traditionally, a cycle bridge would have either a concrete deck, possibly a steel plate deck with an epoxy coating, or even a timber decking. Now, what we've gone with here is actually a product that's 93% recycled. Okay, so that's a mixture of recycled bamboo and also almost 50% recycled plastic. So I don't know if anyone's been tracking the latest kind of news on plastic. I mean, there's a TV program on at the moment called War on Plastic. Plastic is a big issue at the moment. We're chucking away plastic bottles left, right, and centre, and it's just being left for 100 years. So trying to get those materials, getting them uses beyond their normal life is quite important. So we've got a product here that we use, which was 93% recycled. We teamed that up with glue laminated timber, which again is an FSC, which is Forestry Stewardship Council. Ultimately, what that says is this is a sustainable material. So both of those materials combined created a lightweight element that meant the steel, the cables, everything was working that less hard. So that led to the economic kind of driver, which obviously led to a happy client. So all of those things combined well together. We believe, compared to the specimen design, we cut about 50% of the steel out of this bridge. So specimen design was a steel truss with a steel deck and epoxy topping. That was around, we estimate around about 50 tons. This structure, with the superstructure and the mass, came in at about 25 tons. So, you know, if you're going to take anything away from today, it's think about how your material choices can influence the environment and step beyond just the technical aspects and think long term. Okay, let's get into the nitty gritty then of the structural stuff. So the structure was modeled in SAP 2000. At the time, we were running version 20. I know we're pressed for time, so I'll just leave that table up there. You can always come back to this. Essentially, everything was pretty much run non-linear. The cables were all designed as catenary cable elements in SAP, and all the steel and concrete was designed, modeled as beam elements, and we had a variety of different spring types to model variation in the soil. Now, pedestrian dynamics is cool, but it's a big subject, and we could be here all night talking about it. So I'm just going to cover it very broadly, and again, just give you some of the inputs. If you ever come to design a structure similar, just gives you a starting point to work from, and you can come back to these slides. So essentially, we're designing this bridge to Eurocode 2, which is the UK annex, which gives real good guidance on pedestrian dynamics. The first thing you do is you identify the bridge class. So this particular bridge, being close to a stadium, was classified as a type C, which is an urban route. And the difference in your classes just goes to kind of defines the amount of pedestrian density you can expect. Once you define the class, it gives you two types of things. One is a walking group, and one is a running group. And it also defines a limitation on the acceleration you should expect. So in this case, we were limited to 1.3 millimeters per second squared. We had to model to prove that those excitations didn't exceed that. Now, the reason you do that is because that acceleration represents a comfort level to a pedestrian or a user group. So I don't think I actually had a chance to do it. No, I was going to put a model up there showing how we modeled the pedestrians. But fundamentally, we tracked a load. It was a sine wave load. So it kind of tries to represent pressure going up and down at each point along your bridge. And then you have a stride length. So what you're modeling on the bridge is literally a group of pedestrians walking along the bridge. And the video of it's quite cool because you actually see this bulge in your structure as the group moves along. Now, what you can see in the top right corner there, that is the accelerations experienced at midspan. So you can see very to the left there, that's when your pedestrian group is at one end of the bridge. And as you can see, as they're reaching midspan, that's as the acceleration's increasing. Now, within the modeling, we confirmed that we were at 0.9 millimeters per second squared, so we're well within the criteria. But like I say, it's a very cool thing to look at, and I was trying to capture some videos for you, but I ran out of time. Now, I can't really cover much more than that at this stage, but at least that gives you a bit of a segue into that kind of design technique. Wind dynamics, again, because this is a long span cable structure, wind dynamics, pedestrian dynamics, they're all very important elements. So we designed the wind on this one to BD49, and the cables were designed to the Post-Tensioning Institute's cable stay recommendations for cable oscillation and stuff. Now, fundamentally, BD49 looks at your natural periods of vibration, mainly in the vertical plane, lateral plane, and the torsion. So the one I've got there is just the torsion behavior of this particular bridge. Now, when I was looking at the torsion, we found that we were getting some anomalies. And what became apparent pretty quickly is it was very important how we modeled our cross beams. Now, we've got very deep cross beams, and that wasn't being shown in our modelling. So in this instance, we've kind of replicated the deep beam as a truss so that we can get all that torsion through those members. We also did it with rigid links as well to prove similar kind of behaviour. So the key with that is just making sure, again, that your model makes sense. You know, looking at periods of vibration is always a good check. You know, if you really want to test a model, turn on your modes, and if nodes are flying off in the distance, it means they're not connected. It means they're wrong. So it's always actually a good litmus test for any bridge is, you know, we've talked quite a lot today about making sure you understand what you're saying. So checking vertical reactions, I mean, that's a given. You have to be doing that by hand. But checking mode shapes is also quite important. Now, I won't dwell on this slide too much. Really, this is, if you get to a structure similar to this data will give you a starting point. Okay, so as an example there, BD49 is split into 3 main sections. First section is, do you have a structure that you can use BD49 on? If not, you're sent to do wind tunnel testing. That's expensive, timely. Your client's not going to appreciate it too much. So if you can get your initial kind of, it's only a few little calculations in that section 1. If you can get your structure compliant with BD49, you're in a good position. Section 2 is some real high-level checks. If you comply with those, you're all good to go. Great. But if you don't comply with those, then you're into section 3, which is a little bit more complex. So you can see here, I've highlighted one of them orange, which is vortex excitation. So this was in the vertical plane. It's about how much kind of bounce you get with the wind coming through. Now, we failed our section 2 check. Not an issue, it just means we need to do more calculations. So then that led us on to 3.1. That then looks at, okay, so you're getting excitation, but again, it puts it back to a comfort level to your pedestrians. So for this one, for instance, we found that at almost 50 kilometre per hour winds, we'd get what was classified as unpleasant performance. Now, for a lightweight economic structure, we thought, well, that sounds reasonable. If you're out riding your bike across bridges in 50 kilometre per hour winds, you're expecting an unpleasant ride. So, you know, so again, that's about the sanity behind what the numbers are telling you. You know, it hasn't failed. There's a conversation with the client there to explain that. But the way you all chuckled means that obviously it's an easy conversation to have with your client. We don't need to add more stiffness, add more this and that. We can just have that conversation and come up with a simple analogy that they can understand and accept as well. So there's probably minutes somewhere where they've said, yeah, that sounds good, Dan, thanks very much. So I won't dwell on it, but these numbers, like I say, these actually tell you some of the output numbers we received. So if you're doing a structure similar, this will give you a scale or a starting point that at least you can compare. That's one of the hardest things to find in this kind of realm of the dynamics is that starting point. What have other people done? There's a lot of literature on it, but no actual direct examples. Okay, so we're doing all right for time. So the next lot is just a load of slides from construction all the way through to completion. So on the left there, you can see the H-piles. These are driven H-piles going into the ground. And then once that was done, we cast the abutment beams. So they're off in the distance. And in the foreground, that's the dead man anchor. And what you can see on the left and right there is the ducts coming out, in which we had reed bars that once they're out of the ground, then connected with a pretty sophisticated assembly to our cables. And there's room in there for stressing. There's an image there of the fabrication. Now, we were blessed with fabricators that cared. You know, they were passionate. They wanted the details to be right. You know, if we had flange connections, they talked to us about having butt connections, butt welds, so everything's sleek. And everyone wanted this to be something they could take their family and friends to be proud of. And that went through the whole chain, including fabricators, piling crews, everyone. And that's quite important for a successful project. If you can get teams that care, anywhere in engineering, it's worth keeping hold of. You can see there, that's the superstructure being placed. We had to use 2 300-ton cranes to place it. Now, it is only a 45-metre span, but there's also an existing culvert running alongside the water relief that we weren't allowed to put cranes on. So it extended the reach even that further. So I think we were outreaching about 50, 60 metres. So that bumped our crane up pretty quickly. So 2 300-ton cranes on site with the tandem lift. Here we go. So this is, again, HML fabricators down in Blenheim, fabricating the mast there. So it's a beautiful looking thing. And seeing it in the yard, they were all really pleased with it. This image on the right, that shows the pure steel skeletons. This is before any balustrades and timber plastic decking has gone on and any cables are in place. That's just formwork. So that's to the side of the abutment beam there.
You've got the big I-beams on the side of the bridge, and then in the finished example, it's got timber.
Yeah. So I'll come on to that. That's the next bit. So here you go. There's your timber. So, so what we tried to do there is obviously we need load transfer from the decking into the cross beams, but you don't want your decking running all the way between cross beams. The span's too great. So we've used a timber joist type methodology. Now on the sides, we've kind of exaggerated the joist depth a little bit so that we get that architectural appeal. So it's the outside beams are obviously deeper than they really need to be to act as pure joists, but that's a decision that you need to make sometimes. That treat engineering as a craft rather than just a number crunching exercise. Obviously, you can see there they're arriving on the truck. The balustrades were pre-installed, again, just to reduce safety at height issues and things like that. And they're beautiful pieces of kit. So these are glue laminated beams fabricated in Napier by Techlam, and stainless steel fittings, really, really good looking elements. Now here's the cables going on. Like I said earlier, 2 sets went onto the main span before the timber and the decking went on, and also a back span set. What that did is it meant we didn't need to design the superstructure with any pre-camber. We let it sag. We then put the cables on to kind of lift it back up, take some of that weight, and then it was ready to receive more dead load. You can see here we've preferred cables rather than rods. Rods are quite widely used. We've gone with cables, and we've been able to use cable clamps there with a ram assembly. Now on those outrigger cross beams, we've got an extra hole, so there's always somewhere for the ram to connect. And those clamps, I think they're designed for 15 tons, and typically we're pre-stressing to about 10 tons. And you see there, it's a pretty mobile, easy to use kit, so that worked really well. And then it came to the finishing, so we've got beautiful approach handrails. You can see there what that is. That's a very economic but still pretty nice looking balustrade. So we've got a timber glue laminated post, we've got a stainless steel top rail, and we've also got stainless steel mesh infill. Just to kind of what we found is the steel with the timber with the stainless steel, they kind of showcased each other. When you match the timber with the stainless steel, they really kind of bring out the best in each other. So there we go. There's a whirlwind tour on how to design and build a cable stayed bridge. How much? That bridge cost 1.4 million. Originally it tendered at 1.2, but we added extra architectural lighting and there was an increase in the balustrade. But I think ultimately it came in at 1.4, but that's with design, geotech. That was a design and construct price, 1.4 million. So yeah, I'm not sure if the contractor would want to do it again for that price. But yeah, no, yeah, it was a very. The contractor did come away happy, and the client came away happy. The design team did. Everyone came away happy. Now, I think for any project to be a success, you have to have every party coming away having it been a success. Otherwise, it's not really a success. It's no good if the client's upset or the contractor's upset. It needs to be a success for everyone, and this was a good example of that. So yeah. Any other questions?
For a structure like this, would you generate some sort of maintenance program to ensure that you're going to reach your targets of lifespans and all that?
Yeah.
Is there one in place and is it being implemented?
Yes, and actually there was such a big thing on this because it's a marine environment. We've actually got the maintenance plan on the cover drawing. So there's a schedule table. We've kept it as simple as possible so it can be used, but it literally talks about key items. So for instance, the cables. The cables had, I think, around about the 50-year life. So what it says is the table is very clear. It says cables, 50-year life, refer to drawing XYZ. And on that drawing, they talk a lot more detail about the cables. There's a similar one for the timber. So the glue laminated timber, that's got a 50-year life. But the overall structure has a 100-year life. And same with the paint systems. So these were 40-year paint systems. So that cover table, so we had this discussion with the client because they wanted a maintenance report. And we were like, well, what are you going to do with it? It's hard enough getting as-built drawings from the council. So realistically, the only thing that ever really survives with bridge projects, if at all, are the drawings. So that's why we've got these tables on our drawings, so that You know, we could waste time writing in a whole report on stuff, but it's ultimately it just needs to be something simple. And in 40 years' time, they know that the paint, you know, might need extra coats, timber will be replaced and things like that. And those are also stuff that the detailed inspections. So detailed inspections occur, say, every 6 years. And any good inspector will look at the drawings. So they'll see this table and they'll be able to make those recommendations based on what we as the designers are saying.
Any more questions?
Well, I got off lightly, did I?
Impressive project done. Thank you very much.
Thank you for having me.